This is Chapter 1A, Statistical Studies and Producing Data. Chapter 1 is a longer chapter, so it's broken up into 4 parts, A through D. As we work through our Open Intro Statistics text, you'll notice longer chapters have been broken up into 2, 3, or 4 parts. At the beginning of each activity in our packet, we read about why we're studying these particular topics covered in this activity. So in Chapter 1A, you see that we're reading about how we collect, organize, analyze, interpret, and present data. And the next part is the learning objectives. So these cover what you're going to be able to do when you finish this activity. So here you'll be able to distinguish between the questions about a population and questions about cause and effect. You're going to be able to determine if a study is an experiment or observational study. You'll be able to explain how the study design impacts the types of conclusions that can be drawn. You'll be able to identify the sampling plan for a study, and you'll be able to identify features of an experiment design that control the effects of confounding. On the front page of each chapter breakdown, I've put the vocabulary words that you'll see most often in this chapter, along with their definitions. These are meant to be here for an easy reference. So if you're working through the example problems or the group work problems and you are forgetting what a vocabulary term means, you can come and look it up here on the front page of that activity. The vocabulary can also be looked up in your textbook in the index at the back of the book, so that's another option if you're forgetting a statistics term. So make sure you've read through this vocabulary. If you haven't yet, now's a good time to pause and read through our vocabulary for this section. And then we'll look at example 1 together. So example 1 lists different types of research questions. So the first research question type is making an estimate about the population. So I've broken these down as question 1 and question 2 and enumerated the rest of the questions for references. So the second type of research question we might ask is a claim about the population. So you'll see here they're saying, is the average greater than 12 units? Does the majority, meaning more than half? Another type of research question is comparing two populations. So in the community college question, we're comparing female students and male students. Those are the two population groups. You could compare college athletes and non-athletes as two different populations. And the fourth type of research question here is if you're investigating a relationship between two variables. So they give the examples with the number of hours high school students spend on GPA or spend on Facebook as one variable, and then their GPA as the second variable. Or if a student sees an academic counselor as one variable, and how fast they complete their college degree as the second variable. So take a minute, pause if you would like, and read through these research questions more slowly. So A here is asking us to make a list of all the populations in these different research questions. So question 1, the population is community college students. That's the bigger group that we're trying to hypothesize about. Question 2, the population is U.S. college students. Question 3, community college students again. Question 4 is also community college students. Question 5, they're comparing female and male community college students, so that's where they're treating them as two populations. Similarly, in question 6, it's two populations of college students, athletes and non-athletes. Question 7 asked about high school students, and question 8 asked about college students. So sometimes the research questions will just say college students in general. In those situations, I do tend to assume they're talking about college students in the United States. Sometimes they'll specifically say students in the U.S., students at universities in the U.S., students at community colleges in the U.S. But for the most part, we can assume they're typically talking about students in the United States. So B asks us to write a research question where the population is single parents. So there are an infinite number of possible research questions you could write here. The question I wrote is, are single parents more likely than coupled parents to cook at home? So this question compares two populations, single parents and coupled parents, and then we'd have to design an analysis to see how often they cooked at home. Example 2 looks at research questions about cause and effect. So Cause and effect relationships are studied with experiments. Common disciplines that use experiments are medicine or psychology. So these types of questions ask how one variable responds as the other variable is manipulated. So something is intentionally manipulated or changed. And cause and effect relationship questions have two variables. One that is what we call the explanatory variable causing the change, and then the effect is the response. So for each of these cause and effect questions in the table, we want to think about the two variables. So does smoking cause lung cancer? In that case, our variables are smoking, and you'd find out, yes or no, whether or not the person is a smoker, and then lung cancer, whether or not they had lung cancer. Does talking on a hands-free cell phone distract drivers? So here, talking, whether or not they're talking on the hands-free cell phone, is one variable. And then being distracted or not, or you could find a way to measure level of distraction. If you were the researcher, that would be our second variable, or our response variable, we'd say. We'll study more about explanatory and response variables a little bit later. Do people who meditate every day have less anxiety? So here the variables that we're measuring would be whether they meditate daily or not. And then again, we'd have to find a way to measure the level of anxiety. So that would be something that would come up in the research design of the survey, is how are we going to measure anxiety and determine their anxiety level, or just whether or not the person has anxiety. Do antioxidants prevent cancer? So there the variables would be eating antioxidants and then whether the person developed cancer or not. And that would be a pretty tricky study to design. So it'd be interesting to think about how you would design that study and how you would define antioxidants. B asks us to write a cause and effect question where the variables are speeding while driving and the number of traffic tickets. So again, there's an infinite amount of possible questions you could ask here. The question I came up with is, does driving over the speed limit regularly cause drivers to receive more traffic tickets? C asks us to write a cause and effect question where the variables are heart disease and drinking red wine. So the question here I came up with is, does drinking 1 glass of red wine per week reduce heart disease? And then question D asks us to write a cause and effect question where the variables are eating vegetables and colon cancer. So I said, does eating vegetables regularly reduce the risk of colon cancer? So in a research study, you'd have to define what does regularly mean when we say we're eating vegetables regularly. How are we going to measure the risk of colon cancer? What medical issues would be considered risks for colon cancer? So a study for any of these research questions would have to be very well defined and very clearly defining what we mean by eating vegetables regularly. What do we mean by reducing risk? Example 3 looks at 2 statistical studies, and we have to determine what types of studies they are. So you want to look back at the vocabulary definitions for observational study and experiment, because we'll rely on those to determine if each of these studies is an observational study, an experiment, or it could be neither of those studies. So study A is finding 100 women aged 20 who do not smoke, randomly assigning 50 of these 100 women to the smoking treatment and the other 50 to the no smoking treatment. Those in the smoking group smoke a pack a day for 10 years, and those in the control group remain smoke-free for 10 years. Measure and record lung capacity for each of the 100 women. Analyze, interpret, and draw conclusions from the data. So study A is definitely an experiment. These 100 women are intentionally assigned to smoke or not smoke in an attempt to find evidence for a cause and effect relationship. And then I put a note here, this study would be unethical. So typically, any sort of research study at a university or any sort of medical study goes through several review boards to determine if it's an appropriate study, if it's ethical. Anytime you're doing any sort of study with human or animal subjects, you have to go through an ethics board. So this study would never pass an ethics board because, you see, we're randomly assigning women to smoke or not to smoke, and we know from medical research that smoking causes health risks. So this would never be an experiment that would be ethically conducted. Study B, find 100 women aged 30 such that 50 of them have been smoking a pack a day for 10 years and 50 of them have been smoke-free for 10 years. Measure lung capacity for each of the 100 women. analyze, interpret, and draw conclusions from the data. So study B is an observational study. Individuals who smoke and don't smoke are found, and then the variable of interest, which is their lung capacity, is measured. So this would be the kind of study that we could ethically conduct. So smoking is a good example of something where it would not be ethical to conduct an experiment. So we can't ever say for certain that there's a cause and effect relationship in this case, but the evidence is so strong from the many, many observational and health studies that have been conducted that we effectively conclude that smoking causes lung cancer without a cause and effect relationship for sure from an experiment. So there are some situations where we overwhelmingly have so much data from many, many years of observational studies that we can conclude that there is a relationship. Typically, we have to have an experiment before we can say there is a cause and effect relationship, but something with overwhelming data from the observational study, the medical and scientific community says there is a relationship. Example 4. So here we're looking at what's a population versus what's a sample. A political scientist wants to know how college students feel about the Social Security system. So notice I underlined here how college students feel, because she was vaguely saying she's interested in college students. She didn't specify which college or which type of students. She obtains a list of the 3,456 undergraduates at her college and mails a questionnaire to 250 students selected at random. Only 104 questionnaires are returned. So what's the population in this study? Or in other words, we can say, which group does she want information about? So in this case, the political scientist is interested in the thoughts of all college students. So I said I think the population could be all U.S. college students. And then what's a sample? So in other words, what group did she actually obtain information from? So she got information from 104 students at the political scientist college are the sample. So the sample is only the part of the population we have data from. And it is a little risky if you're trying to make predictions about all college students to just use students at one college. So she may want to expand her study to include students from other colleges around the country. In example 5, a hardware store emails a customer satisfaction survey to people who make credit card purchases at the store. This month we know 45,000 people made credit card purchases. Surveys were emailed to 1,000 of these people, chosen at random, and 137 people returned the survey form. So we want to know what's the population. So the population is this larger group of customers who make credit card purchases at the store. And the sample is just the 137 people who return the survey form. So remember, the sample is only those customers we have data from. So even though 1,000 people receive the survey, they aren't part of the sample unless they've returned the survey and we have data. Here's some more vocabulary, so make sure you pause the video or go back and read through this vocabulary in depth. And let's look at some examples using this vocabulary. So example 6 asks us to compare sampling methods. So we're told LMC wants to gather student opinions about taking the bus to campus. It isn't practical to contact all students on campus, right? They wouldn't all respond. For each of the following sampling methods, we want to explain what sampling method is being used and whether or not there is a bias. So A is a woman standing in front of the cafeteria, now and then stopping students to ask them questions. She explains that she is collecting student opinions to see if they will change the bus route from BART. So this is definitely a voluntary response sample, and it's also a convenience sample. So the survey is going to be biased to people with strong opinions because it's voluntary response. So those with strong opinions will be the ones likely to stop and answer the survey. And it's also going to be biased towards the people easiest to reach because remember, she's standing in front of the cafeteria now and then stopping students. So this would not be a desirable study design. B, a computer randomly selects 50 students and emails them the survey. So this is what we call a simple random sample because each of those 50 students is equally likely to be selected from all of the students. Since not all students are required to respond, there will be voluntary response bias for this survey towards people with strong opinions. Anytime you have an optional survey, you're going to get people with strong opinions, either strongly positive or strongly negative, responding. One thing that is often used as a technique to get people to respond, whether or not they have a strong opinion, is to offer some sort of incentive. So you've probably all been at Target or Walmart or another store where they ask you if you'd like to take a survey at the end to win a chance for a gift card or a chance to win an iPad or a chance to win an iPod. So the reason those incentives come up is to try to get people with all opinions, not just people with strong opinions, to take the survey. Question C. A computer program sorts students into categories by ages 17 to 19, 20 to 22, 23 to 25, 26 to 30, 30 to 35, 35 to 40, 40 and above. The computer program randomly selects 200 students from each category and emails them the survey. So this is what we call a stratified random sample, since the population is grouped into similar age groups. Since not all the students are required to respond, there will be voluntary response bias towards people with strong opinions. Example 7 is about how we design a study. So the research question, which is where we start all study designs, asks, does participating in group work improve a college student's comprehension of course concepts? So the professor designs 2 studies. Study design 1 polls 100 college students at campuses across the nation using this question, do you feel that you learn better when working in a group? And study design 2 identifies 10 sections of a typical college course from colleges across the nation. They use group work in 5 of the classes and not in others. Give a short quiz at the end of each class to test understanding of one key idea presented that class period. So we first want to think about, for these studies, which remember they're tied to the same research question, what are the explanatory and response variables? So the explanatory variable is participation in group work, and the response variable is comprehension of course concepts. When we look back at the research question here, we see it saying, does participating in group work, so that's what we think is the explanation, improve the college student's comprehension? So this is our output or our response from the research question. So which of these studies is the observational study and which is an experiment? Study 1 is an observational study since the individuals are polled, but they're not manipulated and the courses aren't changed in any way. Study 2 is an experiment since the group work is intentionally manipulated into the sections. So depending on which section the students are in, they're somehow manipulated into using group work or not. The population is college students across the U.S. nation. And then in study 1, the sample is 1,000 students who were polled. In study 2, the sample is the students in the 10 different sections. So we don't know how many students are in each section. If it was 30 students per section, it could be 300 students. It could be each section is a different amount of students. And study design 2 is going to have some confounding factors. So one of those is different course topics. They just said typical college courses, but there could be a big difference between a math course structure and an English course structure or any other topics. And then the instructors are going to confound the results of study 2. Since you don't have instructors all in the same instructors or at the same school, you've got people all around the country, you're going to have confounding factors due to the different styles of the instructors and the different actual instructors and student responses to them. Confounding factors tend to mix up a study or are other factors that might come in and influence that relationship between the explanatory and the response variable. So we have to make sure we're thinking about those in our study design. Example 8 examines a study. So this is a real study from 2012. Take a minute and pause the video and read through this study since it's a long one. And so question A is asking, is this an experiment or observational study? So this study is definitely an experiment since the diets were intentionally manipulated. In your reading, you saw that people were broken up into 3 different diet groups: low protein, normal protein, and high protein, and then intentionally fed those diets. What are the explanatory and response variables? So here, the explanatory variable is what level of protein the subjects received in the diet. The response variables, there's a few. These are the different outputs that they measured. So they measured the body composition, the resting energy expenditure, the total energy expenditure, and then the weight change. So if you dig back through the research description, you'll see that I underlined here the outcome measures. So that's where I'm finding these answers. Question C asks if there's a control group in the study. So since all participants were assigned this level of protein to eat, low, normal, or high protein, there is not a control group here. So you could argue the normal protein group is a control group, and I would take that as a reasonable answer as long as you explain your reasoning. But since they're also forcing those people to eat a certain diet, I'm going to say, in my opinion, there's not a control group here, because we don't know that the people would normally have eaten what they're calling the normal protein. So what are some of the confounding variables? So if we look back at the descriptor, in the design, we're told here it's single blind. They randomized the participants chosen. There was 25 healthy, weight stable male and female volunteers. They were aged 18 to 35. They had a body mass index between 19 and 30. So these are all factors that the researchers were trying to control for. So the first note I said is that since the study was single blind, this attempts to control patient bias but not researcher bias. So remember, single blind is where the patients don't know what group they're in, but the researchers and the doctors interacting would know what group they're in. Healthy, weight stable men and women were selected, so the study attempted to control for health-related issues and any gender differences by selecting men and women. Participants were ages 18 to 35 years old. So age-related health issues were attempted to control also. They didn't have people over 35 who would have aging-related issues. And then participants had body mass index 19 to 30. So issues related to being very athletic and having a low BMI, or being overweight and having a high BMI, were attempted to control. They just chose a middle range of BMI for the participants. All right, example 9 is a vocabulary check. So we're looking here at different variables to determine, are they discrete random variables? So discrete random variables have numeric values that can be listed and can be counted, but there's a finite list of possible outcomes for a discrete random variable. Continuous random variables have numeric values that can be any number within an interval. And then I put an important note here that the word random means that the outcomes are uncertain in the short run, but they can have a regular distribution or predictable pattern in the long run. So when we talk about random in statistics, this is the kind of definition we mean. If I toss a coin, I don't know in this particular toss if it's going to be heads or tails. It's going to be random. But long run, I do know the coin should come up heads about half of the time. So in statistics, we reserve the term random variable for quantitative variables. And this can be a little bit confusing because categorical variables can also describe random outcomes. So when we say random variables, meaning discrete random variables and continuous random variables, we're talking about numerical or quantitative variables. And you'll hear me use the term numerical and quantitative interchangeably. So it just means a number variable, not a category. So you'll notice all of our random variables here are numerical or quantitative. So our first example, X is the grade point average for a randomly selected college student. So this is continuous because within that interval of 0 to 4.0, you could have any possible average depending on the combination of courses the student had taken, right? You could add up and get any average out there. You're not limited. X equals wattage of a randomly selected light bulb at the hardware store. So this is discrete because if I go to the hardware store, I can't get a light bulb with wattage 92.7 watts, right? We're limited to just whole number values that light bulbs are manufactured in. So since there's limited values, that's a discrete random variable. X is the amount of money in a randomly selected bank account. So I'd say that's continuous. We'd probably round to 2 decimal places, but rounded to 2 decimal places, we could have any possible value in there. X is the height of randomly selected individual trees in a redwood forest measured in feet. So you could, if you randomly selected a tree, it could be any possible height, right? And depending on how precise your ruler is, or if you're using a laser, you could get to a very small, precise decimal measurement of the feet. So those trees could be any possible height. So I'm going to say those are continuous also. X is the average age of a group of students in a randomly selected class at LMC. So even though a student's probably only going to tell you their age in a whole number, when we start to average, any value is possible, right? Depending on what combination of ages we add up and how many people we're asking, we can get any possible average within our interval of what we expect to be a reasonable range. So an average age is continuous. Even though if you just ask someone their age, they're probably only going to tell you whole numbers, which would be discrete. When we start averaging, we could say, oh, the average age in our class is 25.2 years old. X is the number of apartments in a randomly selected apartment building in the Bay Area. So you're only going to have whole numbers when you're counting the number of apartments. So that's discrete, right? You can't have any possible decimal value. X is the number of black marbles in a jar of 500 randomly selected marbles. So again, that's going to be discrete because you're not going to have a decimal part or a fraction part of a marble, presumably. X is the average distance in miles a randomly selected group of 10 students live from LMC. So here we've got an average. So anytime we've got an average, even if students are only reporting their mileage in whole values, the averages can be any possible value. So that's a continuous example. Part B here gives us some graphs and asks us to classify these as discrete or continuous random variables. So part B, the first graph is the grade on the quiz. So I said this is discrete because I'm assuming only whole number grades are given. So if I ask you a question like this, you want to explain your reasoning so that I can see how you came up with your answer. It could be maybe a student argued, well, the teacher could give any possible decimal of a grade, although I've never seen that. And then I might say, okay, that's a fair reasoning, and you'd still get credit. The second graph is the blue crab weight in kilograms. So this is continuous, and notice the graph is really smooth here. So this could be any possible value because when you put the crab on the scale, there's any values possible, and then the scale could get as precise as we're able to in terms of as far out as the decimal goes. And then for the earthquake magnitudes, I said discrete because it looked to me like the values were limited to the tenths place, but you might argue here that this is continuous because you might say researchers could measure earthquake magnitudes to as exact as they want. So I kind of tried to look at the scale down here, and it looks like they're counting by 0.2, so I wasn't sure. In a histogram, it could be, a 1.1 earthquake goes in here, but I wasn't sure if they went to any possible decimal place or do they stop at the 10th place when they talk about earthquakes. Example 10, we're looking at the scatter plot here. So this scatter plot comes from a survey of 193 Duke University undergraduate students. And then this is also an exercise in our textbook, page 59. So you'll see in our activity packet, I've put in some of our textbook exercises. And then in your group work and homework, sometimes you'll be working textbook exercises also. And in those cases, I've pasted them into the packet here, so you don't have to go look them up in the textbook. So in the graph, the first thing to notice is that the X or horizontal axis is measuring study hours per week. And the vertical axis is measuring the grade point average. And we see the range is from 2.5 to 4.0. So the first thing we think about is what's the explanatory variable and what's the response variable. So typically the horizontal axis is our explanation because that comes first, and our response is typically on the Y or vertical axis. And so here we're looking at if there's a relationship between study hours per week and the GPA. So we say the explanatory variable is study hours per week and the response variable is GPA. Question B asks us to describe the relationship. So I'm going to say this is roughly linear. It's not super linear, but if I look at the trend, it's kind of roughly going up in a linear trend. I could say maybe if I had more data points, I could say, well, maybe there'd be a bit of a curve, but it looks like it's kind of very roughly linear. We'll talk later in the semester about how rough we can get and still have a relationship. And then it's got a positive slope because as the study hours per week increase, overall the trend is that the GPA is going up. So you'll notice this is at a positive angle or an increasing slope. There do appear to be a couple unusual cases with high and low GPA for students who didn't study much. So up here, there's a student who had above a 4.0 GPA but studied less than 20 hours per week. And then there was a student that studied a little bit and had a very low GPA also. So there's some unusual cases out here. This is an observational study since the students were not manipulated, right? This would be a hard one to design an experiment around someone's grade point average. And then without an experiment, we cannot conclude a cause and effect relationship for certain. So we can comment on trends that we see, and we'll see how we can do statistical analyses about whether or not there's a relationship and the strength of the relationship, but we do need an experiment to make a conclusion for certain. The next pages are the group activities, so you want to work through those group problems and post in our discussion forum about that.